Hi everyone, this is Xueting Yan from Facebook AI. I'm very excited to have the opportunity to share my work on learning generalizable visual representations with my mentor and colleague Dipti Gadiram. So today I will start my part with a brief self-introduction. I started my undergrad at UIUC, and after that I went to grad school at UCLA, where I came across the computer vision domain at the VCLA lab. After graduation, I went to Facebook, and at Facebook AI, I had the opportunity to work on the intersection of multiple domains, including computer vision, machine learning, and recommendation system. Currently, I'm working on a set of problems, including large-scale representation learning, visual signal mining in recommendation system, and multimodal learning. If you're interested in my work or interested in the opportunity at Facebook, feel free to reach out to me. Next, I'll focus on the talk on one piece of our work at CVPR 2020, which is called Clusterfit, Improving Generalization of Visual Representations. Dipti is also my collaborator there. The problem setup is the following. In learning visual representations, there are usually two stages, one pre-training stage and one final transfer learning stage. In the pre-training stage, we usually use a proxy task such as hashtag prediction in weak supervision or rotation angle prediction in self-supervision as a proxy task to do the learning. However, proxy tasks usually force the model to learn some task-specific information, and this kind of information may hurt representation learning itself. In this work, we ask a simple question. Is there a way to avoid such overfitting to the proxy objective during weak or self-supervised pre-training? In order to solve this problem, we propose a simple framework, Clusterfit. We start with a pre-trained network NP that is trained on some pre-training task. Given a dataset, we first use a pre-training network to extract features. Then we apply k-means clustering in the embedding space. Finally, we train another network, NCF, from scratch using cluster assignments as labels. To check the transferability of the learned representations, we use public benchmarks in transfer learning to test the performance. Here in the pre-training setup, we leveraged fully supervised setting, weakly supervised setting, and even self-supervised setting. In all three settings, and in both video and image domains, we have seen significant improvements in various transfer learning tasks. Also, we apply Clusterfit in a variety of Facebook internal applications. As a generic representation tool, it helped vision understanding, text understanding, and therefore the ads recommendation system. Also, the large-scale clusters can be leveraged as a data augmentation tool, where OCR, segmentation, hate speech, and attribute learning benefit from it in data collection stage. Now I will hand over to my colleague Dipti, who will talk about how to overcome bias in learning visual representations.
Thanks, Shooting. Hi, everyone. My name is Deepthi, and I'm a research scientist at Facebook AI Applied Research. My research interests are on topics related to computer vision, machine learning, and image and video processing. I've been at Facebook AI for 3 years now. Prior to this, I was at UT Austin working towards my PhD dissertation on image and video quality assessment. Here at Facebook, I'm currently working on building fair and inclusive computer vision models, and I'm also generally interested in large-scale visual understanding. And I'm really excited to be here today and to present our work on contextual bias. This work was done in collaboration with Krishna, who interned with my team last summer. This work was accepted at CVPR as an oral. So a lot of existing datasets inherently have co-occurrence bias. For example, in MS COCO, a popular benchmark dataset for object detection, around 98% of images of skateboard always co-occur with person, compared to only 2% of images have skateboard occurring without person. Such severe skewness in the training data leads to a model that has two key issues. The first issue is that the model learns to classify skateboard by unintentionally relying on person. That is, it tries to learn from the wrong thing. Second issue is that the model fails for cases where the person is absent. Our aim was threefold. We wanted to overcome these issues and improve the performance when a category occurs without its co-occurring context. We wanted to maintain performance when it does occur with context, and we want to do this with limited supervision, meaning we don't want to use any bounding box or localization information. First, we quantify contextual bias for a class B as a ratio of average prediction probabilities of class B when it occurs with and without the co-occurring class C. For example, context bias for ski due to its high co-occurrence with person is defined as a ratio of average probability of ski in images with and without person. We use this formulation to identify pairs of biased categories in a given dataset. We call our proposed method as feature split. The key idea of this method is to selectively suppress context when biased class does not occur with its co-occurring context. During training, our method takes images and class labels as input. Note that these images will have, for example, ski occurring exclusively or ski co-occurring with person. We then extract features using a standard network such as a ResNet. We then split the feature space into two equal parts. If the image contains category with its co-occurring context, we use the entire feature space for classification. On cases where images occur exclusively without its context, we use only one half of the feature space and freeze the second half. This forces one part of the feature space, that is WO, to learn biased class-specific information, while the second part of the feature space, WS, to capture the context-specific information. To evaluate our approach, we create two different test splits called exclusive and co-occur. Exclusive split contains images of biased categories without co-occurring context, while co-occurring split contains images with the co-occurring context. We evaluate our very simple yet effective approach on three different object and attribute datasets. On all three datasets, we achieve gains over the standard classifier when a category occurs without their co-occurring context. More importantly, we maintain performance or even improve performance in one case when categories do co-occur together. Here, I present some qualitative results. All of the images here have objects occurring without its co-occurring context. In the green box, we illustrate a few success cases where our approach was successfully able to recognize objects like skateboard or snowboard without the co-occurring context, but the standard classifier failed on all of these images. The red box indicates common failure cases where both our approach and the standard classifier have failed. Common failure cases are challenging scenarios where image has poor lighting or objects are very small. So in summary, a lot of computer vision datasets inherently have co-occurrence bias, where pairs of objects co-occur together very frequently. We proposed an approach to overcome the issues that arise from such co-occurrence biases. And our approach helps improve performance on datasets, on classes where the categories occur with its co-occurring and without its co-occurring context, while maintaining performance when the two classes do co-occur. Finally, I'd love to stay in touch we'd love to stay in touch. So reach out to me or Shooting about any potential internship collaborations at Facebook AI. As Shooting has already mentioned, like some of the topics that we both are interested in are multimodal learning and or building fair and inclusive computer vision models. Here is our contact information. Reach out and stay in touch. Thank you for this opportunity.